Right. So, in this lecture, we will be talking about the Laplace transform of a signal x of t. Okay. So, for a continuous time signal x of t. Okay. So, for a continuous time signal x of t, the Laplace transform is defined as. Okay. So, let me use the acronym for that. So, Laplace transform is defined as. Okay. So, it is defined as x of s is equal to integral minus infinity to infinity x of t into e power minus st dt. So let me call this equation 1. Okay, so here what is s? S is some complex number which can be written as sigma plus j omega. Okay, so s is some complex number which can be written as sigma plus j omega. So let us substitute this s in this equation 1. So what do we get? So left hand side, let us keep it as x of s. Okay, so that will be equal to integral minus infinity to infinity x of t into e power minus sigma t into e power minus j omega t dt. So if you clearly see that, so this can be written as, okay, so this is nothing but, this implies what? X of s is nothing but continuous time Fourier transform of x of t into e power minus sigma t. So that is nothing but continuous time Fourier transform of x of t e power minus sigma t. So when will this exist? This exists, correct? So this exists. If you remember the Fourier transform, when will a signal has Fourier transform? It has Fourier transform if and only if that signal is absolutely integrable. Here we want the Fourier transform of this whole guy. So when will the Fourier transform of this whole guy exist? Only if that fellow is absolutely integrable. So what do we say? This exists if and only if x of t into e power minus sigma t is absolutely integrable. Okay, it is absolutely integrable. So what do I mean by that? So we say that integral minus infinity to infinity modulus of x of t e power minus sigma t dt should be less than infinite. That is what we mean by absolute integrability. Okay, so if this condition is satisfied, okay, so let me call this fellow to be 2. Okay, so if this condition is satisfied, what will exist? This flow will exist. This flow exists means x of s exists. Okay, so indirectly what does it mean? Laplace transform exists if and only if x of t e power minus sigma t is absolutely integrable. Okay, so we will take an example. Let us try to find the Laplace transform of this signal x of t equal to e power minus at u of t. Okay, so how does the plot of this signal look? So if you look at the plot of this signal, it looks something like this, provided the equation of this curve will be e power minus at. Here we assume that a is greater than 0. Similarly, how does the plot look if a is less than 0? So if you look at the plot, it is exponentially increasing function. So both. Okay, so this is again e power minus at, but this is the case when a is less than 0. Okay, so this signal, so with the condition when a is greater than 0, so this signal will have continuous time Fourier transform, whereas this fellow does not have continuous time Fourier transform. That's clear. Why? Because this is an exponentially increasing function, so it's not absolutely integrable, and hence its Fourier transform does not exist. But for this signal, it's an exponentially decaying function, so obviously it will converge, and hence it's absolutely integrable, and hence its Fourier transform exists. But look at the Laplace transform, these two signals will have Laplace transform, so we can assume that the Laplace transform of a signal is just an extension or generalization of the Fourier transform of that signal. Okay, so if let us try to find the Laplace transform of this signal, so what will happen? X of s will be equal to integral 0 to infinity e power minus at into e power minus sigma t into e power minus j omega t dt. So why is that? Why is the integral limits have changed? Because of that u of t function, right? So u of t will exist only from 0 to infinity. So this, if you write in a neat way, so this will be equal to integral 0 to infinity e power minus of a plus sigma t into e power minus j omega t dt. So we can write it like this. If you assume that a plus sigma, okay, let us assume that a plus sigma as b, so clearly, so this implies what is x of s? So x of s is nothing but continuous time Fourier transform of its signal e power minus bt into u of t. Correct? So we can assume, we can easily see that x of s is continuous time Fourier transform of e power minus bt u of t. Okay, so let us proceed with the evaluation of the Laplace transform. Okay, so when will the Fourier transform of e power minus bt u of t exist? Correct. So CTFT of e power minus bt u of t exists. Okay, if you recollect from Fourier transform, if and only if b is greater than 0. But what is b for us? That is nothing but a plus sigma, right? So a plus sigma should be greater than 0, right? Or what is greater, what should be greater than, what will happen to sigma? So sigma should be greater than minus a. But what is sigma? It is nothing but real part of s greater than minus a. So CTFT of e power minus bt u of t exists if and only if real part of s greater than minus a. So indirectly, if this condition is satisfied, okay, if Fourier transform of e power minus bt u of t exists, so indirectly what does it mean? Fourier transform will converge. Okay, that's the reason why this condition we call it as region of convergence. Okay, so this is called what? Region of convergence. Okay, so we call this as region of convergence. Obviously, if this condition is satisfied, then what do we get? X of s is nothing but 1 by b plus j omega. So this will be equal to 1 by, what is b for us? It's already there, a plus sigma plus j omega. So this will be equal to 1 by s plus a. Okay, so let us summarize the result. What is that? E power minus at u of t will have 1 by s plus a as a Laplace transform with ROC real part of s greater than minus a. Okay, it's a very important result, so let us put that in a box. Okay, so it's a very important result, so let us put that in a box. Okay, right. So let us take one more example. Okay, so let us take one more example. So what is that? Let us take x of t to be minus e power minus at u of minus t. Okay, so x of t equal to minus e power minus at u of minus t. So how does the plot of this guy look? Again, we will consider two conditions. So what is that? When a is less than 0, when a is less than 0, obviously plot will look something like this, right? So this will be our minus 1. So this is our t, this is our x of t. So equation of this curve will be minus e power minus at, but for what case? A is less than 0. When a is greater than 0, how does the plot look? Correct? When a is greater than 0, so obviously it will be an exponentially decaying function, so it will look like this. So equation of this curve will be again e minus e power minus at, but this is the case when a is greater than 0. Clearly for this CTFT exists because it's absolutely integrable, but for this CTFT does not exist. Okay, so CTFT does not exist. So let us try to find the Laplace transform of this sequence. So what will be our x of s? So clearly because of u of minus t, so my x of s will be integral minus infinity to 0 e power minus at into e power minus sigma t into e power minus j omega t to dt. So if you simplify this, or if you write in nice form, so this will be equal to minus integral minus infinity to 0 e power minus of a plus sigma into t into e power minus j omega t dt. Okay, so let us, for this problem, let us assume this fellow to be some c. Okay, you'll understand why we have taken that in a moment. Okay, so that is, let us assume that that fellow to be equal to c. So this, if you look at that clearly, we can see that this is nothing but CTFT of which guy? E power CT u of minus t. Correct? CT, oh, this minus sign is there, let us keep it out. So that is nothing but minus CTFT of e power CT u of minus t. So when will this exist? This exists. Okay, so this exists if and only if c is greater than 0 or minus of a plus sigma is greater than 0, or from this we get sigma less than minus u. So this is nothing but what? Real part of s less than minus u. So again this will be our region of convergence. Okay, so that will be our region of convergence. So if this condition is satisfied, what will be our x of s? So x of s will be equal to 1 by c minus j omega. Minus is there, we'll keep it like that. So this is nothing but minus 1 by minus a minus sigma minus j omega. So this is nothing but 1 by s plus a. Okay, so that is nothing but 1 by s plus a is the corresponding ROC given by real part of s less than minus. Okay, so let us summarize the two results. Okay, so what was the previous, so let us summarize this first. So what is that we have seen? So we have seen that minus e power minus at u of minus t will have again 1 by s plus a as a Laplace transform with ROC real part of s less than minus a. So again this is an important result, so let us put that in a box. Okay, so these two are very important results obviously. To get used to that, so let us take few examples. So what is that? So let us try to find the Fourier transform of the following signals. Okay, so first one, I want the Fourier, sorry, Laplace transform of the following signal. So first one, e power minus 3t u of t. So can you guess the answer? So this will be 1 by s plus 3, and what about ROC? Real part of s greater than minus 3. Similarly, if you have another signal like this, e power 4t u of minus t. So this fellow will be, here note that the minus, if you compare these two guys. Okay, so this fellow and this fellow, minus sign is missing, so this will be minus 1 by s minus 4. Okay, so with ROC, real part of s less than 4. So that is one of the ROC. Next, third one. Okay, so we will take e power minus 4t u of minus t. Okay, we'll take minus also. So this is exactly similar to the this one. So what will I get? This will be 1 by s plus 4 with ROC, real part of s less than minus 4. Okay, right. So these are good examples. Now let us take a little bit complicated example. So what is that? Fourth one, will take e power minus 2t u of t plus e power minus 4t u of t. So what will be its Laplace transform? So this corresponding Laplace transform will be, for first one it will be 1 by s plus 2, plus second one it will be 1 by s plus 4. So what are the corresponding ROCs? Real part of s greater than minus 2, and for this it will be real part of s greater than minus 4. So when will the overall x of s converge? Only if both the converges. When will both converge? Only if real part of s is greater than minus 2. So let us see that how it is possible. Real part of s greater than minus 2 is this, and real part of s greater than minus 4 is this. Obviously when will both converge? When will both converges? Only if region of convergence is real part of s greater than minus 2. Okay, so we will both converge only if real part of s is greater than minus 2. So similarly, so corresponding x of s will be what? So if you simplify this, this will be 2s plus 6 by s plus 2 into s plus 4. So this will be the x of s for fourth problem. So now we'll take fifth one, e power, we'll take minus e power minus 2t u of minus t plus e power minus 4t u of t. So clearly again, what is the Laplace transform for this? 1 by s plus 2 plus 1 by s plus 4. So what is ROC for first guy? Real part of s less than minus 2. ROC for second guy, real part of s greater than minus 4. So when will both converge at? So for example, if you take real part of s greater than minus 4 will be this, and real part of s less than minus 2 will be this. So when will both converge? Both will converge only in this region. So what will be the ROC? ROC will be minus 4 less than real part of s less than minus 2. So obviously what will be our x of s? X of s will be equal to again 2s plus 6 by s plus 2 into s plus 6. The corresponding ROC is this. Okay, for this problem corresponding ROC is this. Note that the signal given in fourth and fifth problems both will have same Laplace transform, but they differ in the corresponding ROCs. Okay, so we'll take a final example. Sixth one, minus e power minus 2t u of minus t minus e power minus 4t u of minus t. So for this again, what will be the Laplace transform? Again Laplace transform will be same, 1 by s plus 2 by 1 by s plus 4. But what happens to the ROC? Initially for this fellow, this will be real part of s less than minus 2. For this it will be real part of s less than minus 4. So what will happen? Overall ROC will be equal to how much? Clearly it will be real part of s less than minus 2. So corresponding x of s will be equal to how much? 2s plus 6 by s plus 2 into s plus 4. Sorry, here also it should be s plus 4. Okay, so clearly what is that you observed? Fourth signal, fifth signal and sixth signal, all three will have same Laplace transform, but do they differ? They differ in the corresponding ROCs. Okay, so this ROC is different, this ROC is different, and this ROC is different. Okay, so ROC plays very important role in determining the Laplace transform of signal. So we'll postpone the discussion of properties of ROC into the next lecture. Thank you.